It is pleasure for me to present our new speaker at the seminar, Andrea Ottolini from University of Washington, Seattle. His scientific interest lies in random graphs and mathematical aspects of quantum physics, but today's talk is named Hidden Times in Random Graphs. Please, Andrea.
Perfect. Thank you. Thank you very much for the invitation and everyone for being here. Oops. Okay, hope you can all see. Okay. So as I mentioned, I'm going to talk about hidden times in random graphs. So here is a bit like the outline of a talk. I'm going to start with the warm-up version. Namely, I'm going to talk about the Erdős-Rényi case. And then we're going to move to like some more interesting model, the stochastic block model. And I'm going to talk about the connection with community detection, even if in this sense, I'll try to make it precise. The results are not like exciting from the point of view they're like better than existing results. It's just a curious and funny fact that you can use hidden times to determine like detection of communities. And then I'm going to fit both these examples into a wider framework. And hopefully some of you who have a better knowledge of random graph can help me see whether what are the limitations or the praise of this model. Okay, let's jump with the first case, the Erdős-Rényi case. So this is the problem in a nutshell, as I have a large graph and I move it random from one point to another. I was not expecting this level of excitement. Okay, so here how it works. I have like a large structure, and here I was borrowing on personal experience when I was delivering pizza in a town, and I'm not that old, but back then I still didn't have Google Maps, so I kind of had to move at random. And so you move from one street to another, picking one uniformly at random at each step, and you want to know how long does it take to hit a given target. And the question is then, can we reconstruct the city structure if we know how long does it take to hit a target, like from various starting position? Okay, so let's be a little bit more mathematically precise. So I considered an Erdős-Rényi random graph on n vertices and connectivity parameter p. And I'm gonna mostly work on the case where p is fixed. So I'm happy to discuss on like what happens when p goes to 0. But so what I care about is a very dense regime. And then I look at the time that it takes for a simple random walk to go from one vertex to another. I'm gonna denote this by TWV. And here is how it looks like if you plot. So what I'm plotting here is I'm varying the starting point, fixing a target vertex V. I'm varying the starting point W. And I look at how many points, how many starting point will have a given expected value for the hidden time. There is a story of why I started caring about this problem that I don't have time to jump into. But let's put it this way, when I first made a guess about what the picture was going to be, I was not expecting to have two spikes. So it took me a while to realize why do we have these two spikes. I was expecting some kind of like Gaussian behavior or something. But no, so that's what you got. And so this is a picture for a fixed realization of a graph. So I realized like one single GNP, and I see this kind of interesting and funny concentration phenomenon. And then I started to like think about it, and eventually, if you start varying the parameter, you see that there is some pattern. So let me point out two things at least from you can notice from this picture. The first one is that roughly the two spikes are like of the same size, are roughly in the same position, sorry, which is around like 1,000. Well, n is 1,000, so probably there is some n going on over there. And then if you look at the gap, well, the gap is essentially 2. And now you have a p equal a half. So you may guess there is some like 1/p going on. And this prediction will be confirmed the moment you start to vary the p. So it seems like the things roughly occur at n. So roughly takes n steps to go from one vertex to another. And then there is this little gap of 1/p. And we were able to prove it and get some more understanding of that. So this is the result that I proved in a joint work with Stefan Steinerberger also from University of Washington, which goes as follows. So you take P fixed between 0 and 1. So think of like P being a half. And then with high probability, given a realization of the graph, the expected time to go from the vertex W to the vertex V. So I want to point out that here the expectation is taken with respect to the random walk. So this is still a random variable, right? In the sense that the graph is random. So there's going to be a random variable. And we have a formula for this random variable in the limit, which is twice the edges over the degree, which again, it is a random variable because the edges and degree are actually random. There is a -1 correction and then a 1/p correction that depends on whether V and W are adjacent or not. And then there is some error term that goes to 0. So if you look back and over here, this makes sense because twice the edges over the degree, well, if you think about that's just the inverse of the stationary distribution, which is the answer that you would have got by picking vertices at random instead of going with random walk. But then actually you are taking random walk, so it's going to take slightly longer if you start from a vertex that is not adjacent to V. That's sort of the intuition behind the statement here. Is there any question about the statement? Let's scan through.
And what is E? 2E
E is the number
divided
E,
by...
Yeah, E is the number of edges in the graph.
So N? And what is N?
So N is the number of vertices.
Vertices.
Yeah, vertices. So twice the number of edges over the degree is roughly N, up to square root of N fluctuations. Yeah. So just to put also some context with the literature, the first result that I've seen in this direction show actually that so that there is a bit of an history that I didn't have time to survey, but at first, like physicists care about this problem. And the heuristic was that the answer should be the same that you get by picking IID from the graph, in which case the answer should be N, essentially. Just like twice the edges over the degree. That should be the answer. And then I found this like kind of next order correction. But yeah, so it's twice the number of edges over the degree on a graph on N vertices. So in particular, the first part doesn't depend on P. So you won't see the effect of P, but when you zoom in, you see this like gap, and the gap like has to do with P.
Excuse me, here we have this random variable absolute value of E, number of edges. And does it can happen, for example, that we have such a very small number, such that our graph is simply connected like tree, and then what happens with this T? Maybe then we have the smallest value of steps. How it depends on the distribution of E. Yeah.
Oh, yeah, you're saying, so this one is just for Erdős-Rényi random graph. And now I'm going to talk about how to generalize this to like more general graphs. And I think I have a decent understanding that I'm going to try to convey on like what happens with kind of very homogeneous graphs. The moment you start to be kind of like too geometric, then the proof won't work, but I'm going to try to explain that. So here is just Erdős-Rényi with parameter P. So it's a very kind of homogeneous. Okay. So,
also a short question about the statement. Is the error term independent of vertices, or it depends?
Oh, the error term that I have over here, I can make it so that in here, as with high probability for every pair, so the error term in this case is actually uniform over all pairs. Yeah. This log essentially appears from some maximum of binomial random variables. So I take all possibility of possible pairs. Yeah.
Andrea, do I understand correct that numerator 2 absolute value of E approximately equals NP?
Correct. The top twice the number of edges is roughly N square P, and the degree is roughly NP. So the P simplifies. So the first term
P simplifies also.
Yes.
I see.
So that's why in first approximation, you just see the fact that the graph has roughly all vertices behave the same. So you just see N.
Okay, thanks.
Okay, that's why in this picture you would get like 1,000, and if you change p to 0.3, you still get like things happen around like 1,000, but the gap will change. Okay.
Yes, thanks.
Great. Okay, so in average n steps to reach any given destination, and then there's like this 1/p connection, as I was mentioning. Okay, so let me convince you in 1 or 2 slides of like why the result kind of makes sense, and it's all a question of like looking at the graph in the right perspective, sort of. So if you have a Erdős-Rényi on the graph, let's say on 6 vertices here, the way you should think of is if you fix a vertex, you can kind of split all the other vertices in neighbors and non-neighbors. What is particular about Erdős-Rényi in this case, which I'm using, is the fact that with for fixed p, with high probability, the diameter is actually 2. Either either 2 vertices are either neighbors or they have a common neighbor. Which also gives an intuition on how you may hope to generalize this when p goes to 0. So in general, we have a full understanding of the diameter of like an Erdős-Rényi random graph in all kind of regimes of p. So the moment you see the graph and look at this, the hope is going to be the following. So imagine that at some point your random walk is in region B. What I would like to say is that the chance of moving from region B to region A, it's going to be relevant where you are exactly. So what I would really like to do is forget about the defined structure of neighbors and not neighbors of the vertex V and just collapse this to like 2 single vertices. And then if I can do that, which of course I need to argue in some way, and it's going to be the technical part, then things become easy because now I need to compute hitting times on a 2-state Markov chain. And you can figure out what are the transition probabilities. And roughly, so how many neighbors of V do you have? Well, it's roughly you have a fraction of P of them. And how many are non-neighbors? Roughly a fraction of 1 minus P. And if you believe that the graph is kind of any vertex is kind of like that you end up as kind of random, then the chance of ending up like in any given region is proportional to their size. So here I'm using something about the quasi-randomness, or really in this case, like randomness properties of the edges. So edges between B and A kind of like behave randomly. So if you take any given vertex in B, roughly a proportion that goes in A, the proportion that goes in B is proportional to the respective sizes. So that's the idea. And once you have this, things become very easy and you can justify the formula. So let me elaborate a little bit more. So let me give you essentially the proof. So the idea will be, first I need to find one configuration for which I can exactly compute. So one starting point for which I can exactly compute a hitting time. And this can be done with a little trick, which is if you start from vertex V, so let's maybe go back to the picture here. If I start random walk from vertex V, after one step, I'm going to be uniformly distributed over the set of neighbors. And then by the Markov property, what you know is that if you start from V and you look at the return time to V, which is what I denote by T plus VV, then I take one step, and then I need to look at the hitting time to V starting from this uniform point in the region A. The good thing is that the left side, we know what it is. The left side is just the inverse of the stationary distribution. The return time is just the inverse of the stationary distribution. And so overall, we got a formula for this. So that explains 2 number of edges over the degree minus 1 is essentially explaining the first term in this formula here. And now what I need to convince you is, well, that there is this correction and then there is an error term. And so what do we need to do is, well, we need to show that it doesn't really matter where you start, like within region A, you're always going to get similar average hitting times. So that starting from a uniform distribution on A or starting from any point actually won't make any difference. And that's the technical part, which I'm going to hide because I have a different proof that I want to present that is more general later. But like roughly speaking, what we did is you look at the sort of like definition of the hitting time. So it's defined by some kind of linear system. In this case, it's a random linear system because our graph is random. And you can sort of play a little bit with that and combine some like a priori estimates, and you can do it. So I don't want to go too much into details, but that was kind of like the painful part. Let me put it this way. And then, as I was mentioning, you can separate vertices in neighbors and not neighbors using the fact that the diameter is 2 with high probability. And therefore, we understood, if you believe this, and if you believe that all points within a region look alike, then we understood like the typical point within region A, and now we need to understand a typical point in region B. And to do that, once you have proven this result and show that the two regions can be collapsed, the idea is, well, I look at this three states Markov chain, and I start to compute, well, if I start from B, what should be the hitting time? And approximately, if you start from B with probability P, you jump to like a region A, with probability 1 minus P, you stay. You already know the hitting time from region A. And so as just a matter of like simple algebra, you can deduce that you have this slowdown of 1 over P, which if you look at the picture, it makes sense. It's just, it takes a geometric time with parameter P to go from region B to region A. So that's sort of the heuristic of the problem. As you look at the graph, you realize that the hitting time should be clumped into regions, and within those regions, things should be very homogeneous. Is there any question about this? Are we all more or less happy? I cannot see your faces, so I don't know if any skepticism. So you're welcome to.
Probably a short question
Yeah.
again. So here, as I understand, you work only with the uniform graph. What happens if you put some weights to vertices, and you assume that that the probabilities of depending of edges so depends on that weights? Would the argument work also in that case?
It will in some cases, and that's going to be the general theorem that I'm going to present later. Yeah, but this is just a warm up to say that's roughly the idea. Now, the point is that in a general graph, it's not going to be true, for example, that the diameter is 2. It's not going to be true that you just have like 2 regions that matter. Maybe the graph is more inhomogeneous. So that's exactly the point. We want to understand how robust is this argument. So okay. I'm going to address all these questions.
Okay, thank you.
Okay, great. So one way I like to think of this is that if you have a dense Erdős-Rényi random graph, what I essentially told you is like if you look at the average hitting times, you can reconstruct the adjacency structure in a very concrete way. If you look at this picture, well, I fix the vertex V, and essentially all the vertex W correspond to the first peak. They are the neighbors, and all the others are not neighbors. So you can think of this as reconstructed geometry of the graph using hitting times. So what I didn't like about this proof is that as much as I'm a fond person of eigenvalues and eigenvector and all kind of like spectral results, it is somewhat unsatisfying to use spectral estimates to prove theorems like that, because the idea being the moment you go beyond like Erdős-Rényi random graph, and if I give you like a random graph in the sense of like a literally random graph, like something with like less structure, you won't be able to compute exactly eigenvalues and eigenvectors to the point that we have been using. Now, you may ask, where did I use the spectral estimates? Because I never talk about spectrum. Well, that's hidden in the technical part that I was hiding. So that part relied like heavily on this like spectral estimates and this knowledge of the spectrum of an Erdős-Rényi. And I was fairly unhappy with that. So I try to come up with a better argument, and by better, I mean a more probabilistic argument that bypasses this and that is going to be more flexible. So that's what I want to talk next. And in particular, I want to talk about the how this will apply to the stochastic block model as a further example. Okay. Now, let me talk a bit about the stochastic block model and community detection. I'm going to assume that you don't know anything about a stochastic block model, even though I know it's a lie. You probably know more than me, but just to like not leave anyone outside. So let me start with the quote, which is the motivation for me of like why and how the stochastic block model would arise. So typically I try to avoid examples that borrow from like politics, because people may have like too strong of an opinion. So I'm Italian, and if I have to talk about communities that are very different and hate each other, there is a standard canonical example, which are people from Pisa and people from Lucca. That is a bit of an historical remark for reasons that go back to like 12th century or even before. People in Tuscany can be real intense. Like different cities in Tuscany do not necessarily agree on most of the stuff. And in particular, people from Pisa in the 12th century tended to be the one that like gathered the taxes. And so people from Lucca or other cities were not particularly happy to see people from Pisa showing up at the door, as it is exemplified in this sentence, which translated means it's better to have a dead person in the house than a guy from Pisa at the door. Why am I starting with all this? Is, well, what is the stochastic block model? It's a model in which you have two different communities, and it's very clear that they don't interact in the same way among each other. So I'm going to think of the simplest case, which is I'm going to consider two communities of size n. And I'm going to know that's symmetric in the sense that I'm going to make precise. So I'm going to use this notation for vertices in the same communities, this wiggling sign. So in the stochastic log model, in the simplest possible instances, I'm going to think of like two people in the same vertices being connected with probability P, and two people in different communities being connected with probability Q. And typically, P is going to be different from Q. If P equal Q, you're back to the order 20 model. So this is a more interesting model of a graph in terms of like it creates some kind of like dishomogeneity. You can see two different communities and they talk to each other differently, but it still maintains some property of the order 20 in that it is within communities, things are particularly nice to study. I'm going to talk about just two communities with this kind of symmetry in which both communities have the same parameter P. You can generalize most of what I say to an arbitrary fixed number of communities as long as they're kind of well connected. I'm going to comment more about this. And then I can ask the same question. I give you two vertices. How long does it take to go from one to another? So this is a random variable. Can we find a formula for this? What can we say about it? Okay. So once more, it's all a question of like having the right perspective. So I hope I can convince you with the picture of before or like what the answer should be. So that's how a situation may look like. So here I'm thinking of the green dots being like let's say the people from Pisa, let's say. So I'm thinking of P being greater than Q. So typically people from Pisa are more likely to be friends with other people from Pisa than people from Lucca. And so you're going to have your set of friends in your own community. That's the region A1. But you're also going to have some friends in the opposite community. That's the region A2. And then the region B1 and B2 are exactly the people that are in the respective community, but are not friends with V directly. So that's sort of like the picture you should have in mind. And so in this case, what's reasonable to assume, and again, that we're going to prove it, is that it doesn't really matter in which vertex you are within the region B2, for example. The chance of jumping anywhere else will only depend on the fact that you're in the region B2, and the chance of jumping you can compute explicitly what should be the approximate transition rate to the other regions. So that's the picture then you should have in mind. So the idea of this sort of work is you have a large random graph, you want to reduce it to a small graph with like a simple transition rates and argue that this does not make much of a difference. And then you can sort of figure out what should be the transition rate. This one is a bit more painful to do, but it's still like a 5 times 5 example. So you can work it out like in a page, let's say. So what I find interesting is that you can use the average aiding times to reconstruct both the adjacency structure this time and the community structure. And so here is what I mean. So this is a more recent theorem that I threw this year, which says, okay, so fix the parameters P and Q between 0 and 1. And then you have a formula for the aiding time. Again, this is like a random formula in the sense that the expectation is over the random walks. Thus, this is still a random variable. And it is similar to the one before. So you have a main contribution, which is twice the edges over the degree. So in this case, you still have the degree to be roughly uniform. So there will be roughly n. Then you have a correction depending on whether the vertices are connected or not. That's the same thing that we had before. But then there is also this extra connection depending on whether you're in the same community or not. So if you look at the formula, essentially what you see is that there are 4 possibilities typically, and the one that will take the least, it's, well, if you are connected, if V and W are connected and they are in the same community, that's going to take the least. And if V and W are not connected and they're not in the same community, that's going to take the most. That's roughly speaking the idea. And it's in striking accordance with the numeric, I would say, in the sense that's what happens, for example, where P equals 0.8 and Q equals 0.2. You fix the target point, you vary the starting point, and what you obtain is 4 spikes, and these 4 spikes are exactly the one predicted by the formula. Okay. So let me just like talk a little bit about this connection with the community detection, especially if like some of you work in the field. You may wonder like, okay, how good is this? And the answer is like not much in the following sense. Oops. In the following sense. So if you look back at the theorem, essentially, how can you detect whether the communities are different? Well, you kind of need the error term to be of a smaller order of the gap between the two possibility, whether you are in the same community or not, when roughly that one decays, that goes to 0 as Q minus P squared. So what I'm asking is the moment P and Q become similar, when do I stop seeing sort of a difference in this formula? Well, okay, you do some math, and what you need is essentially Q minus P squared should be up to log factors that I don't particularly care about now. It's essentially, you can go up to 1 over square root of n. On the other end, there are plenty of like clustering algorithms that are based on like other techniques, like spectral or sampling techniques, that actually works all the way to P minus Q being of order 1 over square root of n. So the answer is that you shouldn't use this to do community detection. It's a funny thing that you can do it. I don't think it's because the theorem is not sharp enough. It's just looking at average heating times is not the right idea to detect communities, but it does detect communities if P and Q are sufficiently separated, which is something I found funny, given that the first approximation, you don't see any of this. In first approximation, all these numbers are around like 2000. They don't differ communities, but you see these gaps. On the other end, the point I'm going to try to make is that here I've been talking about a stochastic block model, but really this theorem is much more universal. And by universal,
before you go to the much more universal case, let me ask you the following. Also, let me begin with a joke. When I was a visitor in Cambridge, my neighbor in office was a person from Italy, Mauro Mariani. And one time I asked him about mafia in Italy. And his joke answer was the following. Nobody speak about mafia because mafia is everywhere. So why you choose the same size for communities? What happens if you have different size? Because as I understood, you use some spectral Hebb theorem in order to estimate the speed of conversions to stationary distribution inside of this closet neighbors and non-neighbors. Yes.
No, I do. In this proof, I do not. And actually, this proof would work if n and if the two communities are a different size, as long as they are comparable, meaning that I don't want any of them to dominate the other. As long as they are comparable, and even if the p's are not the same, I can actually prove the same result. So this is purely for like illustrative reasons, because I didn't want to keep track of too many parameters. But you'll see the proof. The sort of like the general statement that I will have in a bit is actually general. So you don't need the communities to be of the same size.
Okay.
Yeah. Okay. So let's talk a little bit about how to make this theorem more general. And so here is the typical situation that I have in mind. So I have a graph G and a target vertex V, and I want to essentially put whatever hypothesis would make a picture like this meaningful. So to do that, what I'm going to say is the following. So I have my graph, which is going to have some technical condition, but the main one is that it's split in like n+1 regions. So one is like a single target vertex, and then you have the other regions. And here's what I'm going to ask. So what I need to ask is that the transition rates from regions is roughly independent of the starting point, meaning that if I'm currently at a state in region I and I want to jump into region J, that should be roughly independent of where exactly I am in region I. That's what this formula is saying, up to a multiplicative error of like order epsilon. And this is what is called a pseudo-random behavior, in the sense that you're saying essentially the, so for example, if you, this is going to work on like weighted graphs as well, but on a single graph, essentially what we're saying is that, so the pseudo-randomness is typically referred to the property that if you have like two chunks of a graph, the chance of going from one to another should be just proportional to the size of this, without really caring where you are exactly. So that the fraction of edges that you have between regions replicate the fraction of edges that you have from any specific single vertex. And then for, I'm going to need some condition about rapid mixing. And I need like rather mild ones, in the sense that this is known as the Dobroshin condition, and is an estimate on the total variation distance between the random walk after one step, between the stationary distribution and the random walk after one step. What is nice about these is that these kind of estimate are very cheap to obtain, are just an estimate on the degrees. You don't need to actually compute any eigenvalues. I mean, if you know about the eigenvalues, you can improve your estimates, but you don't need those. And so this 1/1 minus lambda being order 1 is just a fancy way of saying that lambda shouldn't approach 1. So this is some kind of like rapid mixing behavior. So these are the two hypotheses essentially. And the idea will be to compare the random walk on the big graph to the random walk on a simpler graph, which is what you obtain by collapsing community to a single point. That's sort of the idea. And now I need to tell you what are going to be the transitions in this new graph. Well, the vertices are exactly the vertices that you obtain by collapsing all the points in any given region to one point. And then the edge weights are going to be just the total number of edges that you have between the regions, which is the sort of like natural guess. So the Cij is exactly counting. So it's counting exactly the number of edges between two different regions. And then you need some more technical assumption that I'm going to sort of like sweep under the rug as much as they're actually really important. And essentially, in order for the theorem that I'm about to present to be true, I need some a priori estimate on the averaging times on this smaller graph, which again, in the applications I had in mind, for example, the stochastic block model, are actually very easy to obtain. So roughly what I need to be sure is that I need some kind of a priori estimate that guarantees that in this picture, all the peaks are kind of close to each other. And then my theorem says, well, if all the peaks are close to each other and you have this nice property, this mixing property, then I can tell you exactly how do they space within this region. That's roughly speaking the idea of the theorem. Again, if you, I'm happy to talk more about this, but this is not particularly.
I have one small question about the second Dobroshin condition.
Yes.
Is it possible to obtain Dobroshin condition if you have condition number 1 and if Pij is not degenerate?
Yeah, they're not completely independent. That's a good point. I think yes. Yes, you're totally right. Like the easiest example of like, well, if you know that the Pij
you know that all transition between I and Vi and Vj are close to Pij.
Yes, so that should be yes. Yes. I think it should be possible. Let me think for a second if you don't have any trouble, because definitely this say that like the small graph mixes well, meaning that once you collapse the point.
So if the question, my question is, assume that the small graph is nice. It's finite graph, all states are connected, and assume that it's a periodic. Is it true that the second condition is satisfied?
I I would suspect so. I think it's a bit delicate because you need something about every time. So I guess the argument would be every time you come back to the region, you kind of end up in a uniform random spot. So the idea is that if the Pij don't degenerate, you come back like often enough. And so it should be able to mix with the stationary distribution there. I think some version of it should be true. I don't know if there is some. I found it convenient to assume this because in any example, it was easy to verify this independently. But that's actually a very good point that probably from condition 1, you can get a version of condition 2. You just get a bound on them.
Because if small graph, you may construct some coupling. Some coupling.
I use it the other way, meaning that I was able to show, for example, that the, and actually it's a simple exercise, that the lambda that you have on the bottom, if you look at this smaller graph, you have the same kind of lambda. So I use it the other way. So I use the fact that if the big graph mixes well, the small graph mixes well. But of course, the more interesting one is the small one implies the big one. So I think, yeah, that's actually a good point. And I'd be happy to discuss more because I think that's actually a very good point. Yeah, thanks. Great. Okay. Now I've learned with some experience that like whenever people put like hypothesis and assumption on a theorem, you should be a bit skeptical because the intersection of all the assumption may be the empty set. So I kind of want to convince you that this is not an empty theorem, and this epsilon and lambda that I'm like mentioning, they're actually concrete numbers you can get in some example. So that's an example in stochastic block model. You can actually by hands, and by hands, I mean, this is a type of exercise that you can give as a homework in a class. You can estimate this, and you get the lambda is, in the case I was talking about before, it's essentially 1 minus the average connectivity parameter, and the epsilon is roughly square root of log n over n. So the epsilon, remember, is like how much kind of homogeneous are these regions that I'm using. So you can get your hands on these numbers, and you don't need to know anything about the spectrum of the adjacency matrix of the graph. And this can be generalized in the sense that I can allow more communities. I can destroy this kind of symmetry assumption I put at the beginning. The communities may be of different sizes. You can also modify this example, for example, by starting to, so a classical one is, well, what if like friends of friends are actually more likely or less likely to be friends? So you can add like an additional parameter that favors the number of triangles. It's the same idea. You just need to adjust what is the small graph that you're considering. And again, these estimates typically are not too bad to obtain. When you have like very dense graphs, it's just something about the degree distribution within and across these various kind of communities that you care about. This is an example, for example, with 3 communities. That's the picture that I got. I think I forgot what were the parameters. I didn't list it down, but anyway, this is just to say that this phenomenon seems to be pretty general. You get these spikes that are close to each other. They're spaced in some way, and there are formula for the way they are spaced. And this is a version of the theorem. So if you want a more precise version, you can look up my paper directly, but I kind of like put like a mild version in which I only put the dependence on the parameter epsilon. And it says the following. Let's say that you want to understand the heating time on a big graph. What you can do is you can study the heating time on the small graph in which you start, well, if you were starting from a W that belongs to the ith region, well, you start from I, you want to eat V, which is the 0th region. And the error that you commit by doing this is essentially epsilon, up to floating parameters that depend on distribution condition, but is essentially this error is epsilon. So as long as epsilon goes to 0, things are fine. That's roughly the idea. Actually, if you look at the proof is stronger, and what it shows is that, well, the absolute values is before taking the expectation, meaning I can construct a coupling between the two in such a way that they're going to be very close. So in particular, this is, you can think of this as a result like in Wasserstein 1 distance. So this in particular implies also closeness in distribution. So my result is actually equivalent to say that these 2 heating times are close in distribution and they're close in expectation. Okay. So now what I want to talk about is I'm gonna briefly address something about the proof. And so the idea is to couple 3 walkers. So you start from region VI, and you're going to couple 3 walkers. One is the random walk that you care about, the one on the big graph starting from W. Then we're going to use the random walker starting at stationarity and a random walker on the smaller graph. And the idea is we want to show that we can couple all these walkers so that they're equal, and this will have a number of implications. So as term of notation, I'm going to use the notation gamma of xk equal j to denote that's essentially the region I'm at currently with the random walker. So just to have a picture, usually this is the moment where I use a board, but I forgot it and there's no board here. But so essentially what I'm saying is that I'm jumping over these regions and I'm going to keep track of the region, and that's like my gamma. Okay. And so the goal is to couple the random walker with the stationary walker as quickly as possible, and then to maintain the random walker. So you would like to the Y chain then to follow exactly the X chain, in the sense that the projection of the X chain should be exactly the Y chain. And so my assumption, essentially my lambda and epsilon are equivalent to say that are equivalent to bounds on how well you can do this. So the lambda is related to like how fast you can couple the 2 random walkers, the stationary one and the random walker not at stationarity. And epsilon is related to like for how long you can maintain the 2 chains, the xk and yk, to be the same. So in our application, lambda is going to be fixed and epsilon is going to be small. So it's going to take not so much to couple, and it's going to take a long time before the 2 walkers start to like be driven apart. Okay, then there is a useful lambda that I was mentioning, which is once you know how to couple the walk on the big graph with the stationary walker, you can actually do the same for the smaller graph. So you can couple pretty quickly the a walker on the small graph with the corresponding stationary walker. And because of that, essentially, there are 2 scenarios to consider, which are the following. So either you couple with the stationary walker before the X and the Y chain decouple, and by using this lemma, then we're fine. And we can actually, from that moment, the 3 walkers will always remain the same. So in particular, the heating time to V will remain the same. So this is the sort of easy case. Or things could go wrong. And so what happens is that you're walking around, but at some point, the X chain moved to a region, but the Y chain moved to a correspondingly different region. And this happens before that my walkers kept coupled with the stationary one. So in this case, what do you want to do then? Well, you'll forget about the so once that happened, then what you want to do is you want to recouple the Y chain as quickly as possible with the stationary distribution. And that is then a question of like bounding some geometric random variable. And so let me pack all this together. So it is in the first scenario, there is like nothing that really can go wrong. So now what could go wrong is the following. Either it takes a long, so I want to show that this like tau c are small, and I want to show that this tau d are large, essentially. So the problems could be either this is not true. So for example, it takes a long time to mix with the stationary distribution, or what happens is that it takes a very short time for the chains to decouple, and then they decouple, and before they recouple again, one walker hit the target and the other not. Remember that our ultimate goal is to compare the heating time to the vertex V on the 2 graphs, the big and the small one. So what things that will go wrong is that at some point they're different, and one hit the target and the other one does not. So what about these events where these heating times are different? Well, that's exactly what I was saying, is that, well, you need one of the 2 walkers to hit the target vertex. And by that time, you want the 2 walkers to be decoupled. So that's the K bigger than like the time to decouple, in the time in which the big and the small graph, the random walk on the big and the small graph look different. But then K should also be smaller than the time that it takes to reach stationarity, because we know that once both chains have reached stationarity, actually we're fine. So essentially I need to estimate those probabilities. And now there is some work to do, but essentially you end up, because of your a priori estimates that you have, you're trying to estimate the expected time between these two eating, the expected distance between these two eating times. It ends up just being a question of like total variation distance between these two eating times. So what you need to estimate is the probability of t being different from t prime. And this is going to be small enough that it's going to kill this factor of n that you have. And then you can think of, okay, how do we split this? And as I was mentioning, there are sort of like two different cases to consider, where when k is very large, what you're thinking is that the event that is unlikely is that the time that it takes to couple with the stationary walk has to be very large, and that's kind of unlikely. That's essentially geometric time with parameter 1 minus lambda. So that's going to take care of the k large, while for k small, we're going to use the left inequality here. So the first part of the inequality here, it's like a union bound that says, well, things decouple in a very short time, and then things decouple, and also one of the two walker is the target. What's the chance of hitting the target? Because my assumption is essentially 1 over n. I'm assuming that is a very rare event to hit the target vertex v. On the other side, the second bound that we obtain is just the coupling time being very large. So these end up like being two tail estimates, and you can compute explicitly. Actually, in the first case, we just use a union bound. So you obtain something which is of the form epsilon plus some exponential decay in lambda. Now you want to optimize over m. Turns out that the choice to take is like m being roughly log of epsilon. This is 1 over n factor, and that's how you deduce the bound. So it's a bit hand wavy because there are like some construction of the coupling that actually play a role, but that's essentially the idea. You want to you use the stationarity to take care of the events in which one hitting time. So you take care of the short times by using the fact that like things want to decouple very quickly, and if they do, it's very unlikely that something hit the target vertex very quickly. And then you take care of like, okay, what happens instead if you just like have a long run without hitting stationarity? Like, well, that's kind of unlikely because of our mixing time condition. Okay, so this was like a sketch of the proof. Now let me talk a little bit about some open questions in case you're interested, in case you're working on similar models, you have more idea, which seems to be the case, given that I got already some useful insight. So one thing that is unsatisfying about this proof is that it starts to degenerate pretty quickly the moment you have like sparse graphs. So what do I mean by that is that, for example, even if you consider the error-free random graph, so let me quickly go at the very beginning of the talk if you want. Even in this simple case over here, the moment p goes to 0, this actually degenerates. And with my proof, I'm able to let p goes to 0 up to like n to the -1 over 8. There is nothing particular like a reason why this number should be much nicer than others. It's just like my current like technical limitations. I suspect that the theorem should be true in a more general setting. I just don't know how to prove it using my techniques. So for sparse graphs, something like that should be true. But even in the error-free random graph, I'm not able to handle it. The problem being that my estimates, for example, about a mixing time or the estimates that I have about this parameter epsilon, they're just not good enough. So that's one thing. It would be nice to handle like sparser graph. Also because that seems what people care about the most. Is there a question coming?
I have a question about sparse graphs. So if p is fixed, then with high probability, the graph is connected.
Yeah.
But if p is very small, then probably not, and expectation is infinity.
Yes. So that is so the first thing is that so the connectivity parameter is roughly like log n over n, right? So for p equal log n over n is like when the graph so over that, you know that with high probability you're connected. The problem starts earlier in the sense that even so there are So the first guess you can have is that, well, okay, what's the simplest scenario is you decrease P at some point, the diameter from 2 becomes 3. At that stage, I'm already not able to prove the result that would be intuitively seems to be true, which is, well, I just need to study a 3-stage Markov chain. So what you're pointing out is the problem that happens when you're not connected anymore. My point is that my limitations are much more strict. Like I start to have a problem already when the diameter is 3. Which is why I'm annoyed and I push this at like n to the -1/8. It would be nice at least to push to n to the -1/2, which is the threshold for having a diameter 3. What happens all the way down to like log n/n? That starts to be more complicated. I suspect that something like that should be true. You just like study along longer tree, like a longer path. And my hope is that the argument will go all the way up to the connectivity threshold. And then what you're saying, once you're not connected, surely you need to do something. For example, condition on being in a connected component. And then at some point, things become like a little bit fishy with my proof because, for example, think the extreme case, if the degree is constant at some point, so if you go like all the way up to constant over n, then it's definitely not true that the transition are independent of where you are, because then the degree are going to be Poisson, and actually the average Poisson and like a single one, they're going to be very different. So I think before getting all the way to the, I would summarize this by saying that there is some hope that you can get all the way to the connectivity threshold. Below that, for a variety of reasons, even if you just condition on being in the same connected component, I think this proof is just not the right idea. The hope would be at least to push to the connectivity threshold, yeah. But yeah, so far, this is very weak in the sense of like, I need P to be constant. So that's very restricted, yeah. Okay, so that's one thing. Then another thing I would like to understand is that if you look at the pictures, there are these spikes, and in some way they look like normal. So what do I mean by that? How do you make sense of that? Well, what you could say is that suppose that I have my community, suppose that I start from a random point within a community. Then the hope will be that I get some kind of like central limit theorem. How to prove that? I was not able. So it's related to this error term. If you want, in theorems like that, I have an error term, which is square root of n up to some extra log factor. I suspect that those log factors are kind of fake. And I suspect there should be some limiting behavior after you rescale by this. How to prove it? No idea. If you have some, I'd be happy to talk more. But that's what I mean, like understanding the behavior within those regions and kind of make sense of what kind of picture do you get here. Yes.
Excuse me. What do you think? The reason can be following. You use the very same formula of total probability when you are going near some point. Yes. And this means that if you have some small component of your graph, then you use the behavior which is very like to the some random walk on some regular structure. Then you can use the central limit theorem, of course, to get the fluctuation. Yeah, to estimate the fluctuation. Yes. So this your hypothesis about small graphs, and I think there is hidden regularity of components here. Maybe
Yes.
this is the answer. Yeah.
Yes. Now, how can I? This is related to a point I wanted to make. So it seems that so there are kind of like various. So you're saying that this fluctuation here should somewhat come from the fact that once you fix the sizes of the community, there are fluctuations on the number of edges between communities, if you want. Like that's still like random, and that has something to do. But here I'm looking at a fixed realization of the graph, right? So this does not fluctuate anymore.
But this realization can already have some regularity because of your choice of n and p.
Yeah, that's true. Yes. Yes.
Okay.
Mm. Yeah. No, I see what you mean. Yep. Okay, I'll think more about it because, but let me keep going. Okay, and then another thing that I find funny is that once I add the result, I thought, okay, this is like I just do the L1 norm. How bad can it be if you look at like any other, if you look at like, for example, the second moment of the heating time? My hope was that like, my bounds are good enough, these are going to be good. It seems that they're just not. Meaning that if you look at the variance of the heating time, the proxy of like, oh, I kind of want to simplify the graph and look at the smaller one. The variance come from like the variance of the random walk on the smaller graph. This is just wrong. And I suspect that the idea is that the variance comes in two parts. One is like the fluctuations that you have for the heating time on the small graph, but you also have the fluctuation that come from the fact that I'm assuming here that you always end up like in a sort of like typical vertex. But sometimes maybe you end up with a vertex that has a bit more like edges that go in a certain direction. And so you have a lack of regularity if you want, and that actually seems to contribute to the variance. At least numerically, that seems to be the case. Now, whether there's an effect for small n and my limited ability of simulating things, that's another story. But I suspect they're actually generally different. So if you have to guess a formula for the second moment, I think you need to be a bit smarter than this. You cannot just like collapse points to like a single vertex, which is something that I found kind of curious and funny. So it would be nice to have something more about that. All right. So just wrapping up. Hope you liked the talk. If you're interested, shoot me an email. And let me also mention that if you did not like the talk, you can borrow my own quote about Pisani-Lucchesi, which I'm not going to translate, but if you want, you can translate yourself. Thanks for the attention.
Okay, thank you very much for very interesting talk. And maybe somebody have questions or comments, please.
May I do some comment? And it is about your assumption or your conditions on page 15. It is condition number 1.
Yes, let me go.
About some probabilistic structure of the blocks, right? So as I understand it.
Yes.
So here I have some comment because for me it looks somehow similar to the condition which we have, because together with David and Vlada's image we consider the scaling limit of stochastic block model, and when we consider many blocks, actually when we can find a good description of the scaling limit of sizes of connected components for stochastic block model. In the scaling regime, in the critical regime, it is the following. You must have a graph. So first of all, you can couple your graph and make, the multiplicative coalescence process when you consider the sizes of blocks. So just you can put all graphs that depends on your parameter p. So on one probability space, rescale that parameter, and when you will consider the sizes of connected components, you will come to this to the multiplicative coalescent. And the property which we have there, it looks as follows. Then when you consider on one level up, just actually when you assume that your blocks are vertices and edges between these new vertices appear when at least one edge between members appear, then this must also have the multiplicative structure. Also, it must be a multiplicative coalescent. And when it is the case, then we can describe the scaling limit via exclusion of some random field. So here I see also some properties that also looks like you must have like Markov process, but just considering your blocks. So probably it is the same type of the assumption that we have and you have. And probably there is some more deep reason why this assumption appears. Because, for instance, in our case, it appears because of the technical reason. Probably in your also, because as I understand, methods is so much like related on that assumptions. Maybe you should discuss that with David when you will see him next time. Probably you will have some idea about these assumptions.
Great, because as I mentioned, I'm meeting him on Thursday. So thank you. Thank you. That was actually very interesting. Also, I should mention another example I'm working out is like it's this maybe similar to what you're saying. So the idea is that exactly, it seems that you scale these parameters so that you get some like nice limit in a way. So what I was also thinking, if you take like a graphon, for example, you can use a graphon to generate a graph out of it. And then it seems that if you start with the graphon, which is kind of nice, then you can get some similar result. So kind of like view the point of like take already the limit and construct a graph from there. But yeah, no, this is actually very useful. Thanks.
Okay, and maybe very quickly another question. You already commented that. We know, for instance, when we make P going to 0 and Q also going to 0, and we have also one scaling regime. I mean, when considering the sizes of connected components, we have something non-trivial, like in the work of Aldous about the Ottolini graph. We can do the same with the stochastic block model. In this case, about how stable the stopping time will be under this type of rescaling when you send the number of vertices to infinity, P to 0, you have no idea actually what should be.
I can only work in a very mild regime. I think I mentioned this like P going to like 0 as like n to the minus 1/8, but it should be like, it's not very interesting in a sense that you're still in the regime where the diameter is 2 of the graph. So it's like it's a fake going to 0, meaning you're still like dense. And so what would be interesting is to push this, as I was saying before, up to like a connectivity threshold. But that's our bounds is like to be not good enough. But I use very crude bound in a way because I use like a lot of union bounds. I use like uniform estimate of the maximum of binomials. So there are several parts in which you want to be sharper, depending on the question.
Okay, thank you so much.
Thanks.
Okay, other questions, please? Let me have also some questions. Firstly, when you discuss the heating time, did you think about the loops, the number of loops which you have on the way from one vertex to another?
So it does not seems to be related to the number of loops in first approximation.
Yes, it is not very related, but this number of loops can be a characteristic also of the geometry of the graph you obtained. You said that one of ideas is recover the structure of the graph using this map of the mixing expectation of the mixing time. But it can happen that if you know the number of loops, then you know the structure better. Yes. For example, if you know definitely that there are no loops at any path, then maybe you have a tree. Yeah, something like this.
Yeah, I suspect that it could be so my guess would be that, like, for example, if you look at the formula like these, my hope would be that in the error term afterwards, there may be some effect that is that comes from like a finer structure, like for example, number of loop or the homology group or something. At this stage, the only thing I see is whether you're adjacent or not, and fluctuations of degrees. But yeah, so I agree that it should play a role. If I have a lot of loops, this should have an effect. It's a lower order effect, and it would be interesting to see if you can get all the way up to that. But yeah, that would be my bet, is that if you expand this formula, if you imagine there is an expansion of this formula, I would bet like something like a homology group of like number of loops would like play a role. Then how to prove it and what's the guess for the formula, that's a little bit
Yes, we have good formulas for number of loops and for length of the loop raising wall on the very regular graphs. Like we have a homogeneous random group and so on. Yeah.
So I should mention also, maybe just as a comment, is that you can actually use this. So there are the beautiful relationship by I think is a work by Lovash that connects like heating time, expected heating times to various like spectral properties like weighted sum of eigenvalues and eigenvectors. So you can use this to get some better estimates over there. And I suspect there are a connection between those and like, for example, like structure of the homology group of like presence of loops. So it could also be that some answer already hidden in this like kind of roundabout way. So for example, I can get better bounds on the eigenvalue correspond to the quasi-stationary distribution using my formula. So there are like ways in which you can get your hands on the spectrum using this result. And from the spectrum, it may be that you have easier access to that. So that's another thing.
Actually, this is my next question, because definitely when you have the uniform estimation for heating times, you must have the estimation to the stationary distribution for random walk on this graph. And then do you have something like cutoff effect here? So when n increase, so what can you say about this?
Okay, so in terms of cutoff, so here is more like I use like so the estimate that I use, which is not spectral, but I have this estimate that I need on the time to stationarity that I use. It's kind of off in the sense that, so let me try to explain. So when you look at this condition, the condition that I use, so the second condition about the lambda, so this one is a very suboptimal condition to like how long does it take to reach stationarity. Like for example, for Erdős-Rényi, this thing will be like 1 minus p, which is not capturing, for example, the fact that after 2 steps, random walk on Erdős-Rényi is actually already mixed. So I think because I care about a heating time, I think this does not really say much, this result, about the time to reach stationarity. It's more like I use result to like reach how long does it take to reach stationarity, but I use very soft result in that setting.
Yes, so not in the backward direction, yeah?
No, I wouldn't say so. Yeah.
Okay, thank you very much.
Okay, thanks.
Okay, some other questions or comments? If no, thank you very much for the interesting talk, and hope to see you again at our seminar. So thank you very much, and this is end of our work for today. Thanks everybody, and see you next week.
Thanks a lot for inviting and for following. Bye.
Thanks for a nice talk.
Thank you. Bye.
See you.
Thank you. Bye.
Yeah.
Thank you. Bye.
Bye.